Radiation in Medicine. Risks and Protection, 2. By Assistant Professor of Medical Physics, Dr. Al-Arif. Biological Effects of Radiation. What happens inside our bodies? Photon radiation primarily interacting with water molecules producing hydrogen peroxide molecules H2O2, which goes into more chemical reactions to produce very reactive chemical molecules called free radicals. Free radicals invade and damage the DNA or any other vital critical targets inside the cells by breaking bonds. This can kill the cells or leads to genetic mutations after certain time. There are short-term and long-term effects of radiation. The severity of each depends on the amount of radiation received by the body and the type of radiation. Radiation effects. 1. Deterministic effects, non-stochastic. Deterministic effects occur after relatively large doses of radiation above certain dose, threshold dose, below which no effect is recorded. The severity of the effects may be influenced by individual person and some other factors such as the type of radiation and amount of radiation dose. The severity increases with increasing damage to the number of cells. Example, loss of hair and skin burning, as in the figure.
2. Stochastic effects. There is no threshold dose, starting dose, for this effect to happen. A stochastic effect is one for which the probability of occurring increases with increasing time of exposure, while the severity of the effect is independent on the magnitude of the absorbed dose. Example, developing cancer and genetic mutations, as in the figure. The absorbed dose, d. Absorbed dose is defined as the quotient of amount of energy, E, received by unit mass, m, of the body and the volume of interest of the body, and is given by the following equation. Absorbed dose equal the amount of energy, E, divided by the unit mass, m, in kg. Gray, G, is the unit for radiation dose in the SI system. The Gray is defined as the deposition of 1 joule of energy in 1 kilogram of the matter. 1 Gray equal 1 joules per kilogram. 1 Gray equal 100 rad. Where the rad is the old unit for absorbed dose.
The effective equivalent dose, H sub T. Radiation dose don't gives the real radiation effects on human body since this varies with radiation and tissue types. The ICRP, International Commission of Radiological Protection, recommends to use the effective equivalent dose, H sub E, to describe the whole body effect of radiation due to various types of radiations and tissues included according to the following formula. H sub E equal the summation of the product of the tissue weighting factor, W sub T, by the equivalent dose H sub T. Where H sub T is the equivalent dose representing the amount of radiation dose multiplied by the radiation quality factor, Q, and is given by H sub T equal the summation of the radiation quality factor, Q, multiplied by radiation dose, D. W sub T is the tissue weighting factor, with no units. The values for which are shown in the following tables for different tissue types. Table 1 shows the radiation quality factor for different radiation types. Table 2 shows the tissue weighting factor, W sub T, according to the ICRP 1990. The tissue weighting factor, W sub T, was calculated from the results of the survival of the first atomic bomb in Japan. The results for 1 million of population receiving same equivalent dose, at same distance from the center of the bomb, the number of cases of mutation or cancer developed in different organs followed for 2 generations were recorded and presented in the Table 3. The weighting factor for different organs was calculated by dividing the individual incidents over the total number of incidents. Table 3 shows the number of incidents, cancer or mutation, occur for different organs. For safety purposes, the ICRP recommended dose limits for those working in the field of radiation, occupational dose limit, and for public people for 1 year and is shown in Table 4. Table 4 shows the recommended dose limit according to the ICRP 1990.